In this video, I'm planning on deriving the first law of thermodynamics, so basically an energy balance for open systems. So first of all, why would we need this? Well, we would need this for any process that involves flow. So when you have flow, you have a control volume. So let's say that we have like a pump, and this would be our control volume. So we have flow going into and out of this control volume. So anything that has flow into or out, so think about like pumps, turbines, pipes, compressors. A lot of the systems we're interested in have flow into and out, and we might need to calculate the relationships between thermodynamic properties such as temperature and pressure. So for instance, if you're designing a pump, you need to know how, like, let's say that the pumps in real life are going to generate heat from friction, and we need to know how much heat we need to remove from the pump. So basically, how much cooling does that pump need so that it doesn't overheat or like burst. And so we need to know, like, if we have compressors or heat exchangers or power plants, we need to calculate how much heat we need to remove or put into a system, how much work we might get out. And so basically we need a way that we can calculate relationships between the different thermodynamic properties in open systems. And so that's why we're going to want to apply the first law, or basically an energy balance, to open systems so that we can calculate those things. So first of all, let's just draw a control volume. So here's a control volume. And so I'm going to specify that this is the control volume. And we have fluid flowing in and out. So let's say that we have a mass of fluid right here that's flowing into the control volume. So basically I'm going to draw it here. So this is after it just pops into the control volume. So I'm going to label that this is fluid flowing into the control volume. And then over here, we have the fluid right before it pops out of the control volume. So here's the fluid after it pops out. So this is the fluid mass flowing out of the control volume. All right, so basically we're interested in this mass that's flowing into or out of the control volume because there's a certain amount of energy. So mass carries energy. So when we have the mass flow into the control volume, it's going to carry energy with it. And when it flows out of the control volume, it's also going to carry energy with it. So we can specify this energy here as the energy in, and I'm writing this lowercase because this is energy per unit mass. And then we have the mass that's flowing out, and this is going to have a certain amount of energy associated with it. So we have the energy out. And so what we can do is we can say, okay, well, we have this process of the mass flowing in, and then it's flowing out over a certain amount of time, dt. So I'm going to say that the energy at state 1. So what we want to do is imagine this change with time. So this process of the mass flowing into the control volume, flowing through the control volume, and then flowing out of the control volume is occurring with time. So we can actually draw this as, like, here's our control volume. So this is state 1. We have a certain amount of mass that's flowing into the control volume. And then we have our process or whatever is going on, and at state 2, so this is a change in time, so I'm just going to specify that this is, so I'm going to specify this as delta t, and we have state 2, and at state 2 the mass is flowing out of the control volume. So what we can do is we can say that at state 1, so E1 is equal to the energy that's already associated with the control volume plus the energy that's carried in with the mass, so with this differential amount of mass. And then at state 2, we can say that the energy, or the total energy, is equal to the energy already associated with the control volume plus the energy associated with this mass that's flowing out of the control volume. So we know that E2 minus E1 is equal to the change in energy of the system. So this E is total energy. So right now I'm just talking about the total energy associated with the system. So we know that E2, the energy at state 2 minus the energy at state 1, is equal to the change in energy of the system. So what I can do is plug these into this equation. So then I have that, so E2 is the energy of the control volume plus the energy associated with the mass flowing out, or the differential mass flowing out of the control volume, minus, and then I have the energy associated with the control volume at state 1 plus the energy associated with the mass that's flowing into the control volume is equal to the change in energy in the control volume. So now what we can do is group terms together. So I'm going to group these two terms together and these two terms together. So if I do that, I get that dE CV is equal to E, so the energy associated with the control volume at state 2 minus the energy associated with the control volume at state 1 plus the energy associated with the mass that's flowing out of the control volume minus the energy associated with the mass that's flowing into the control volume. So this ECV2 minus ECV1 is the change in energy of the control volume. And so we have dE is equal to dECV plus, and then we have the energy associated with the mass that's flowing out of the control volume minus the energy associated with the mass that's flowing into the control volume. So now what we want to do is we want to calculate this as on a per time. So we're going to take the derivative with respect to time. So we have dE dt is equal to dE CV dt plus the energy out multiplied by dm out dt minus En dm in dt. So we want to just save this equation for a minute because we're going to use it in a minute. So this is the energy associated with this mass that's flowing into or out of the control volume. Now we want to consider work. So we've been considering energy. Now we want to consider the work associated with this problem. So basically there's two types of work. First of all, there's miscellaneous work. And this is work such as, this is often called other work, so I'm going to also say other work. But this is things like mechanical inputs or outputs. So this could be shaft work, paddle work, electrical work. So I'm just going to say that this is the miscellaneous work associated with the control volume. And I'm just going to specify this is things like shaft work, paddle work, electric, etc. So this would be the other type of work. So this is the first type. The second type is boundary work. So we already know that if we have a change in volume, we have boundary work. So change in volume, a change in our control volume means that there's boundary work. And so this is pretty apparent if we have, say, a piston cylinder. We know that as the cylinder moves, or as the piston moves up and down in the cylinder, boundary work is being done because we have a force, and then we also have the volume is also changing. So the boundary work might not be quite as obvious with the fluid that's flowing into or out of the control volume, but basically, if we look at, say, state 1, when we have fluid flow into this control volume, when we have mass flow into the control volume, there's going to be a volume change, and when the mass exits, there's going to be a volume change. One way to look at this boundary work is it requires work to push this volume of fluid into the control volume, and it requires work to push this volume of fluid out of the control volume. So basically there's going to be work associated with that fluid that's being pushed into and out of the control volume, and this is the boundary work. And so we've already seen the equation for boundary work. The boundary work is equal to P dV, and this is equal to P, the specific volume, multiplied by dm. So dV is equal to the specific volume multiplied by the mass. So basically we get that the boundary work is equal to P V dm. And this represents the boundary work at both the inlet and the outlet. So this is the boundary work at both inlet and outlet. And so at the inlet, this is actually, so if we have, so at the inlet, and I'm just going to write at inlet, so this is the boundary work in, this is going to be negative because the work is being done on the system, so it's negative. So this is P in, and then V, specific volume, D, M in. So this is work done on the system, so it's negative. And then at the outlet, the work out is positive because the work is being done by the system. So I'm not going to write the plus there, but basically this is positive because the work is being done by the system. So basically the work at the inlet is the work that's required to push the mass into the control volume, and the work at the outlet is the work that's being done to push the mass out of the control volume. So what we can do is we can write the total incremental work. So the total incremental work is the boundary work is equal to this is the miscellaneous or other work. So if we go back up to here, we had this as the miscellaneous work or other work. So this is just the work is equal to the miscellaneous work or other work plus the boundary work out minus the boundary work in. So basically this is equal to else. So this is the work. So the other work plus, and then this is P out specific volume dm out minus P in specific volume in dm in. And one thing I want to point out is the specific volume is going to change unless you have an incompressible fluid. So the specific volume will change unless you have an incompressible fluid. So we can't assume that the specific volume isn't going to change. A lot of times in just like a fluid flow class, you can assume that the specific volume is constant because you can assume that the density is constant because you're talking about a flowing liquid. But in this case, we don't know if it's constant. It could change. I mean, a lot of times we're dealing with gases, or we could be dealing with something that's being compressed, or so we don't know. We can't make that assumption until we've looked at the problem. So now we want to take the time derivative. So if we do that, we get the work. So the change in work with time is equal to the change in, I'm just going to put, this is just other work with time, plus P out, V out, D M out, dt minus P in, V in, dm in dt. Alright, so this is our equation for work. Now let's go back to our general equation for, well, basically let's write our equation for the first law. So we know that the first law is, well, it's Q minus W is equal to delta E. And we can rewrite this as dq dt minus d work, dt is equal to dE dt. And so now what I want to do, I'm going to move the work over to this side, so I'm just going to add it over. So then I get that dq dt is equal to dE dt plus d work dt. And actually, let's go back to this equation. I just want to specify what some of these terms are. So this first term is the rate of change of heat transfer. So rate of change of heat transfer. This term is the rate of change of work transfer. So rate of change of work transfer. And then this term is the change in energy with time. So change in energy with time. So what I want to do, so I have this equation. I want to take these equations that I derive for dE dt, so the change in energy with time and the change in work with time, and I want to plug them into this equation. So let's start with the work because it's just right here. So what I'm actually going to do is rewrite these equations that we derived so they're all in the same spot. So the equation that we derived for the work was, and then the equation that we derived for the change in energy with time, so dE dt, and this is just the equation that we derived earlier that I circled and said we were going to use. This is the change in energy in the control volume, dt, plus E out dm out dt minus the energy in dm in dt. So what we're going to do is put these into this equation. So if we do that, we get that dq dt is equal to, and I'm going to start with the with dE dt. So I have dE cv dt plus E out dm out dt minus E in dm in dt. And then this is plus, and then I have this equation for the work. So d work dt plus p out v out dm out dt minus p in v in dm in dt. I want to rearrange this and just group some terms together. So I want to group the energy in and energy out with the PV, and so what I'm going to get is dq dt is equal to, I'm going to actually rearrange sides too, so I have plus, so dm in dt. So I want to combine the two terms, like we have dm dt here, dm in dt here, and dm out dt, dm out dt. So I want to combine those terms. So I have dm in dt, and I have en plus p in v in, that's the specific volume, is equal to, and then I have this term, so d E cv dt plus dm out dt multiplied by, and then this is going to be E out plus P out V out plus, and then I have this work term, so D, and this should be CV. So this is the other work. So work CV dt. So now what we want to do is remember that the energy, so the total energy, assuming that we have a simple compressible system, the total energy is equal to the internal energy plus the kinetic energy plus the potential energy. And we can write this on a per mass basis as this. So E is equal to U plus V squared over 2 plus GZ. So what we can do is plug this into this equation for the energy. And if we do that, we get the dq dt plus the mass in with time, and then this is going to be u in plus v in squared over 2 plus gz in. And I'm going to actually rearrange this. So I'm going to put this P in, V in here, and then plus the kinetic and potential energy. So this is plus, and then GZ in, and then this is equal to dECV dt plus dm out dt, and then I'm going to have the same thing over here, so u out, and then I'm going to put this PV term next, so P out, V out, plus, and then the kinetic and potential energy, so V out squared plus GZ out, and then this is plus this other work term. So now if we look at this, we have, so remember that U plus PV is just the enthalpy, so this is HN, and then we have U plus PV here, so this is H out. And so we can rewrite this using the enthalpy, so if we do that, we get the dq dt plus dm in dt, and then this is multiplied by the enthalpy plus the kinetic energy plus the potential energy is equal to dE CV dt plus dm out dt, and then this is multiplied once again by the potential energy out plus the kinetic energy out plus the potential energy out, and then plus the other work. So basically when we have a flowing fluid, or basically an open system, we end up with this U plus PV term in our equation, and so we can just use the enthalpy, and the enthalpy is going to account for both the internal energy and the basically our PV or pressure boundary work. So now let's use the dot notation for the derivative. So this dq dt, basically I'm just going to say that this is q dot. So q dot plus, and then this is just the mass flow rate, so m in dot multiplied by h in plus the kinetic energy in plus the potential energy plus, and then we have, actually this is equal, the change in energy with time plus, and then this is just m out dot, and then we have h out plus the kinetic energy out plus the potential energy out plus the rate of work. So now we basically have this equation for the general energy balance, but this is for one stream. So we could also write this, so just like the mass balance, we could also write this for multiple streams. And so the way we do that is we have our Q plus, and then we'll have a summation for each stream. So basically we have, so we'll just sum all of the streams in. So this is Hn plus Vn squared over 2 plus GZn is equal to dECV dt plus, and then we're going to sum all of the streams out. And I should specify that this mass flow rate here is in, this one's out. And then the enthalpy plus the kinetic energy plus the potential energy plus the rate of work. So this equation here is the general form of the first law for an open system. So this is the general form of the first law for an open system. And this is only one form of the equation. There are other forms of the equation, so you'll see this equation written different ways. So just try to recognize what the different terms are, and every way that you see it written should basically be the same equation. You'll just see it written different ways. But now what we can do is look at some special cases. So let's look at some special cases. First of all, if we have steady flow, which means that which basically, if we have steady flow, it basically means that there's no change with time. So steady flow, no change with time. And basically what this means is that a few of our time derivatives are going to be zero. So this dm cv dt is equal to 0. So basically what that means is that the mass flow rate isn't changing with time, so the mass flow rate in is equal to the mass flow rate out. And so the rate of mass flow in is equal to the rate of mass flow out. Also, this derivative, so the change in the energy and the control volume with time, is equal to 0. So I'm going to also write that dE cV dt is equal to 0. And then also so basically there's no change in the state of the thermodynamic properties at the inlets and outlets with time. And all of the Q, so the rate of heat input, or the rate of heat input or output and the rate of work input or output remains constant with time. So I'm just going to specify that Q dot and W dot remain constant with time. And so basically the given rate of heat transfer doesn't change. So if we apply all of these things for the steady flow, our equation for the first law becomes Q dot, and I'm bringing the work back over, so Q minus W, because it's usually written as Q minus W rather than how I have it here where I'm adding Q2 at the right side of the equation. So I have Q minus W, and remember these are still rates, they're just not changing with time, is equal to the sum of the mass out and then the enthalpy plus the kinetic energy plus the potential energy minus the sum in, so I'm going to put out on this one. So this is m in dot, so the enthalpy plus the kinetic energy plus the potential energy. So this is the first law for a steady flow open system problem. So this is the first law for a steady flow open system problem. So basically a problem with a control volume. Now let's look at the case for a single stream steady flow. So if we have a single stream steady flow, which is often written as SSSF, we can drop the summations because if we only have one stream in and one stream out, we really only have one, so we don't have the summations anymore. So then we have Q minus W, and remember this is still for the steady flow, is equal to M dot, and then since it's a single stream and a steady flow, we know that M dot out is equal to M dot in. So then we can combine some of our terms because M dot is just M dot. So now we have the enthalpy out minus the enthalpy in plus the kinetic energy out minus the kinetic energy in, 2 plus, and this is out, plus the potential energy out minus the potential energy in. So this is the first law for a single stream steady flow. And this is probably the most common equation used. If you're given a power or a rate of heat transfer, you're going to want to use this equation, assuming that you have a single stream and that it's steady flow, which that's a really common case for a lot of engineering systems. Also, since we know that Q is equal to Q dot over M dot, so this is Q over M, and the work is equal to the work over M dot. We can rewrite this equation as Q minus W is equal to the enthalpy out minus the enthalpy in plus the difference in the kinetic energies plus the difference in the potential energies. So Z out minus Z in. So basically with this equation, so these are for the single stream steady flow. With this one, if you're given power or rate of heat transfer, you want to use this equation. If you're given your work or your heat as a per unit mass, you want to use this equation. So if given data per unit mass, use this equation. Alright, so just going back up to what we've done. In this video, we derived the general form of the first law for an open system, which was this equation. So this is just the really general form of the first law equation for an open system. And then we looked at some special cases. So first of all, we looked at steady flow. So with steady flow, that means that there's no changes with time. So in other words, our mass flow rate doesn't change with time, our energy in the control volume doesn't change with time, and the rate of the heat and work input or output remain constant with time. And then we considered this for a single stream. So this is the steady state single stream flow equation, and this one is probably the most common form of the first law that you're going to use for an open system energy balance. So if you were given, say, power or rate of heat transfer, you would use this equation. And then this equation is the same equation written on a per mass basis. So if you're given your data on a per mass basis, you would use this form of the equation. So in the next video, I'm going to go over how this equation simplifies for various engineering systems, such as pumps, compressors, turbines, diffusers, heat exchangers. So we're going to look at how this equation can be applied to actual engineering systems.